Hello students, welcome to aptdemy. Myself Dr. Nandita, and today we are going to solve some numerical problems of a chapter of chemistry which is atomic models, and the detailed videos regarding the theories along with some numerical problems you can go and check our aptdemy LMS platform. So before going into detail, let's take a quick look on the mathematical formulas that we learned through this chapter. So we learned that the wavelength and frequency of electromagnetic radiation are always related by the following equation, that is C is equal to nu lambda, where lambda is the wavelength, nu is the frequency and C is the speed of light. Later we learned that Max Planck proposed the energy E of a single quantum equals to a constant times the frequency of the radiation, which is represented by the following equation, that is E is equal to h nu, and it can be also written as equal to Ch by lambda. Here h is the Planck's constant and it has a value of 6.626 times 10 to the power minus 34 joules second. Now later Rydberg presented this equation which is known as the Rydberg equations, and this is represented in the following manner, that is 1 by lambda is equal to r times 1 by nf square minus 1 by ni square, where nf and ni represent the final and initial state of the electron. The energy states of the hydrogen atom can be represented in the following manner, that is E is equal to minus hcrh times 1 by ni square, which can also be represented as equal to minus 2.18 times 10 to the power minus 18 times 1 by ni square joule. Here in this equation, h, c and rh are simultaneously the Planck's constant, the speed of light and the Rydberg's constant. The integer n here can have whole number, for example 1, 2, 3 and so on, and it is called the principal quantum number. Later de Broglie proposed that the wavelength of the electron or of any other particle depends on its mass m and on its velocity v, and de Broglie's equation can be represented in the following manner, that is lambda is equal to h by mv. And you can see from this schematic that it can also be written as lambda is equal to h by mc or equal to h by p, that is the momentum. Heisenberg's uncertainty principle states that it is totally impossible for us to know simultaneously both the exact momentum of an electron and its exact location in space. And if delta s is the uncertainty in location and the delta mb is the uncertainty in momentum, they are related through this equation, that is delta x times m delta v is greater than equal to h by 4 pi, and this uncertainty in position and uncertainty in momentum are related to our Planck's constant through this equation. And here you can see from this schematic that order in which orbitals are filled in multi-electron atoms. So these are the quick recap of this chapter. Now let's start the numerical problems. So illustration 1 is asking, the visible spectrum shows the wavelength range from violet 400 nanometer to red 750 nanometer, and express these wavelengths in frequencies hertz, and it is given that 1 nanometer is equal to 10 to the power minus 9 meter. So let's try to solve this problem. So first we will write for the frequency of violet light. The wavelength is given as 400 nanometer, and what we know? We know that nu is equal to c by lambda, right? And c is the speed of light, so we can write in place of c, that is 3.00 times 10 to the power 8 meter per second, divided by the lambda is given as 400 nanometer, and if you present in terms of meter, we can write 400 times 10 to the power minus 9 meter. If you solve, you will get the value of 7.50 times 10 to the power 14 Hz. So this is for the violet light. Now let's solve for the red light. So the frequency of red light, we will use the same formula, that is nu is equal to c by lambda, and just putting the values. Speed of light is again 3.00 times 10 to the power 8 meter per second, divided by the lambda is given as 750 nanometer. That is 750 times 10 to the power minus 8 meter. Right? Sorry, minus 9. So if you solve, you will get the value of 4.00 times 10 to the power 14 Hz for the red light. Now, so we can write that the range of visible spectrum is from 4.00 times 10 to the power 14. What we have got for the red light? 14 Hz to, and what we have got for the violet light is 7.50 times 10 to the power 14 Hz in terms of frequency. And that has been asked in this problem to solve, right? Very simple. Now let's move on to the next illustration, which is saying that determine the energy of 1 mole of photons of radiation whose frequency is 5 times 10 to the power 14 Hz. How can we solve? So we know that energy E is equal to energy E of a photon can be written as h nu. So here we know that h is equal to the Planck's constant, and it is having the value of 6.626 times 10 to the power minus 34 joule second, and the frequency value is given as, that is nu is given as 5 times 10 to the power 14 second inverse, and this is our given data. So for E we can write h nu, that is 6.626 times 10 to the power minus 34 joule second times 5 times 10 to the power 14 second inverse. If you solve, you will get 3.313 times 10 to the power minus 19 joule. So this is the frequency, and this is the Planck's constant, and we have got the energy values using the following formula. E is equal to h nu, and this is having the value of 3.313 times 10 to the power minus 19 joule. Now we have to calculate for 1 mole of photons. So we have to multiply this value with Avogadro's number. So that's what we are going to do. So we will write that energy of 1 mole of photons is equal to 3.313 times 10 to the power minus 19 joule multiplied by the Avogadro's number, which is 6.022 times 10 to the power 23 mole inverse. And after solving, we will get 199.51 kilojoule per mole. Right? So this is the energy for 1 mole of photons. Right? Very simple. Now let's move on to the next one, which is asking that a 100-watt bulb emits monochromatic light of wavelength 400 nanometer. Evaluate the number of photons emitted per second by the bulb. Here power is given. So let's see how can we solve this problem. So the power of the bulb is given as 100 watt. Right, which can also be written in terms of joule per second, that is 100 joule per second. Now we have to calculate for the energy of one photon. We can easily write that is E is equal to h nu, and this can also be written as equal to Ch by lambda. Now let's put the values. So for h, so for C we can write 3 times 10 to the power 8 meter per second, that is the speed of light, times 6.626 times 10 to the power minus 34 joule second, that is our Planck's constant, and the lambda is given as 400 nanometer, that is 400 times 10 to the power minus 9 meter. If you solve, you will get 4.969 times 10 to the power minus 19 joule. Now we have to calculate the number of photons emitted. How can you do that? We have the values of power. This is a 100-watt bulb. So the number of photons emitted can be calculated as the power, that is 100 joule per second, divided by the energy, that is 4.969 times 10 to the power minus 19 joule, that we have obtained above here. And now after solving, the result is 2.012 times 10 to the power 20 second inverse. Right? So this is the number of photons emitted that has been asked in this problem. Simple. Now let's